Okay, so good afternoon. So let me tell you what we will do for the remainder of the summer school, starting this afternoon. We're going to devote it to credit risk. And we have, in the book that you all have, there's a lot of credit risk, but it certainly is one of the most important risk categories, if not the most important risk category. Well, that may depend on what kind of institution you work for, but certainly in banks, the most important risk category. So there are 4 chapters. And we will present material from 10 and 11. So 10 this afternoon. In 10, we begin with section 10.1. There's not much in there. Credit risky instruments. We look at all the different things that are subject to credit risk. But after that, the focus of 10 is on the credit risk of a single firm or a single obligor. So the way the material is arranged, it begins with one obligor. How do we model the credit risk? In Chapter 11, we put them together in a portfolio. So Chapter 11 is portfolio credit risk. Chapter 12, which we won't do, has some material about dynamic models and CDOs. And Chapter 17, which we will get on to in the final session tomorrow, has some material about counterparty credit risk. Okay. So to go right to the beginning, we have a definition of credit risk. This is the one that we put forward in the book. Risk of loss arising from the failure of a counterparty to honor its contractual obligations. So this is quite general, subsumes various things. Default risk, so the risk of losses due to the default of a borrower or of a trading partner or of a counterparty in a derivative transaction. And also downgrade risk, the risk of losses if there's a deterioration in credit quality of a counterparty. Counterparties, you would want them to maintain their credit quality. They have a kind of obligation to you to maintain their credit quality. If their credit quality deteriorates, that may cause you losses. Some words that we will use, this word obligor, which I hadn't heard of in the English language until I started to study credit risk, but the obligor comes from obligation. So credit risk arises from unfulfilled obligations. So the obligor, a counterparty who has a financial obligation, some examples, a debtor who simply owes us money, a bond issuer who's promised us interest and promised to redeem the principal at a later date, should they fail to either pay us interest or return the principal, and a counterparty in a derivatives transaction, where I've agreed with this counterparty to perhaps to make some kind of swap of payment streams, and should my counterparty fail to fulfill that obligation, that contractual obligation, that will be a problem.
So there could be some transactions where both parties are obligors?
Yeah, certainly in a swap, as far as I'm concerned. If I'm in a swap with you, yeah, you're an obligor as far as I'm concerned, and I'm an obligor as far as you're concerned. So default is simply the failure to fulfill that obligation, failure to repay loans, failure to pay interest, etc. And of course, there are various reasons why that default may take place. A liquidity issue, which means the cash isn't available at the right time to make the repayment. A lack of liquidity may be symptomatic of a deeper-rooted problem. The company may be insolvent. That's more worrying because the end result, of course, may be bankruptcy. But a lack of liquidity, a default caused by lack of liquidity is a sign that all is not well in the risk management of this company. So as I've suggested, it's a pretty important risk category, hence the amount of space that it gets in the book. And it arises in all kinds of context in financial services. Obviously, if you're a bank and you have a portfolio of loans, that's clear. If you're an investor with a portfolio of corporate bonds, so not treasuries from very highly rated and essentially non-defaultable countries, but corporate bonds, these are obviously affected by credit risk. And as you will see, and this will be more tomorrow, in an over-the-counter derivatives transaction, such as, for example, an interest rate swap, we will take that specific example. So tomorrow we'll look at an interest rate swap and we'll analyze it, and you'll see where the counterparty credit risk comes from. So if one of the parties doesn't fulfill their contractual obligations, that is a default, that's a loss. Here in this category, in the second category, the derivatives we're talking about, these may be derivatives which are actually designed to manage other kinds of risk. If it's an interest rate swap, it's been designed to manage interest rate risk. So primarily, an interest rate swap is about interest rate risk. Primarily, a foreign exchange swap is about foreign exchange risk. But because it's a contract between two parties, it carries credit risk, counterparty credit risk. Now, there is a third category, credit derivatives, and these are specifically designed to manage credit risk. And so here you have things like credit default swaps. In the book, we look at securitizations as well under this heading, but for today's and tomorrow's purposes, we will just look at the credit default swap as an example of a derivative that is specifically designed to manage credit risk in the first instance. Clearly, banks are subject to a lot of credit risk, but it's very, very relevant to insurance companies. On the asset side of the balance sheet, insurers are exposed to substantial credit risk in their portfolios of bonds. Moreover, there is counterparty credit risk in reinsurance treaties. So in the insurance industry, credit risk is equally a big theme. To finish this introduction, and I should probably keep my eye on time because we're having to apply a bit of a rearrangement algorithm to the structure of the workshop to fit it all in, but I think that will be possible. So credit risk management, what does it mean? The question which is central in the book is the question of capital, determining capital for credit risk, whether looking at the regulatory rules or looking at economic capital that a prudent institution would want to have of its own volition. And then there are, if you have portfolios of credit risky assets, then of course there are considerations of diversification of the portfolio, of optimizing the return, subject to risk considerations, or vice versa. For the credit derivatives, the things like the CDS, there are issues to do with valuation, with hedging, and then perhaps managing collateral for these trades. And so in the second edition of the textbook, a lot of material has been added about this. And counterparty credit risk, this, since the financial crisis, has been a big, big issue for people in banks. They need to control their counterparty credit risk. And so that's why we have a separate session on that to close. 10.1, I'll keep it really brief. In the book, we sort of list credit risky instruments, beginning with simple things like loans and bonds, and then going on to derivatives. But for the purposes of the examples, we will be essentially thinking of defaultable bonds and credit default swaps. And when we come to value things a little bit later this afternoon, we will need the credit default swap. So a little bit about those and related credit derivatives. So as I've said, they're primarily used to manage credit risk. That's the point of the credit derivative, as opposed to some other kind of derivative which is subject to counterparty credit risk. And the payoff will be related to the default of one or more obligors, or one or more firms. And in this chapter 10, it will be related to the default of one firm, because chapter 10 is about the single firm. In this market, lots of participants. Obviously, banks and investment banks are major participants, but also insurance companies will use credit default swaps to hedge credit exposures. And so it's an important thing to know about. In the banking world, you will find the retail banks are typically net buyers of protection. We're going to see that the credit default swap embodies the notion of one party selling protection and the other party buying protection. And so retail banks are generally protecting themselves against credit events, such as the default of large obligors who owe them money. Whereas investment banks and hedge funds, they will often enter on the other side because they see opportunities to make money. The CDS well, it says here, the workhorse of the credit derivative market. And there's a huge volume of these contracts written. And before the financial crisis, the market grew. Through the financial crisis, and it's still a huge, if not an even bigger market since then. So the structure of a CDS, we will look at this picture, but it will come back, I think, when we later on. There are three parties listed here, but only two of them are actually engaging with each other directly. The third party here, the reference entity, is not involved directly. But this is the firm whose default we are worried about, or one of these parties is worried. Party A is worried about the default of party C. So, I don't know, let's pretend that C is an oil company or a supermarket group, or we were in Vive yesterday, or Nestle, a company that issues a bond. It issues bonds on a large scale. And A here is a bank or an insurance company that has a very large holding in the bond of C and wants to protect itself against the default of C. B, the protection seller, comes in and offers that protection. And so what's going to happen is that if there is a default of C, B is going to make good the loss that A would suffer. So if there is a default, so here's a rhetorical question, does C default? If yes, B is making a default payment. If no, then obviously no payment. But the other side of this swap is the premium payments that A makes to B to pay for the protection. A little bit of notation, there will be a maturity, same notation as we've used all week. There will be a maturity to this contract. Tau C is the default time of entity C. It may never default, but we are worried about the event where tau C is less than T. The premiums are paid until maturity, and of course, and they cease should default take place. And the default payment is only made in the event that tau C is less than T. So we'll just...
Premium payment are fixed.
The
variable premiums, fixed premiums.
Yeah, we'll take it to be a fixed premium.
Something like a partial default does not exist?
There may be a recovery. So default, this will be sort of legally regulated by the contract. It will either happen or not. But in the event of default, it certainly may not be a total loss. There may be a recovery. And so a recovery element will probably come in. And a proportion of A's exposure to C may come in.
Maturity is typically 5 years? Or?
Something like that, something like a 5-year CDS. Those are the kinds of time horizons we should think of. So I think what I've said is summarized here, but let's just make sure. So if the reference entity, that was C, that was Nestle here, experiences a default before T, the protection seller makes a default payment to the protection buyer. It mimics the loss, or it makes good the loss that the protection buyer actually experiences. And this CDS, it's said to have 2 legs. And this particular leg is the default payment leg. The compensation, the premium, is paid by the protection buyer to the protection seller. It's a regular payment stream. It might be typically quarterly payments are made. And after the default, premium payments would stop. In this swap, there is no initial payment. It has to be decided at the outset what is a fair premium. So the fair premium or the fair swap spread is decided at the outset. Usually they're quoted as a percentage of the amount of the protection. So you might buy 10,000 Swiss francs worth or 50,000 or 100,000 Swiss francs worth of protection against this reference entity, and the spread premium will be a percentage, and we will use X star as the notation for that when it reappears. The corporate bond I won't explain. That's the other contract, the other instrument that we will value. So just one more slide on the CDS. Why on earth do these things exist? Well, to begin with, it was about protection. It was about hedging exposure to large credit risk. So if you think of the company that invests, so an investor in bonds with a very large exposure to a particular company may genuinely worry about the credit risk. So what they could, of course, do is reduce the bond holding. They could sell out of that bond completely. They could reduce the holding. But the bond market is not particularly liquid, and to sell a very large amount of the company's bonds would probably lead to a loss through liquidity risk. Whereas it is easier to do a CDS. The CDS market is more liquid, so rather than reducing the original bond position, you could do a CDS because they are more liquid. So this was the original reason for CDS. It really was about protection, but then the market very quickly became speculative. The other side, the protection sellers, are doing it because it offers speculative opportunities. And in fact, many of these companies appear in credit default swaps on both sides. So they appear as buyers, they appear as sellers, and they're doing this to speculate on changes in the spread, and to make money in that way. So companies that do it purely speculatively, usually they are actually taking naked CDS positions. So a protection buyer, if they don't own the bond, that's called a naked position. You don't have to own the bond. That's actually the final point here, and that's perhaps surprising at first. You don't actually have to own the bond to buy protection. So if you don't own the bond and you're buying protection, you're speculating basically on the widening of the credit spread. You're speculating on the widening because at a later point, if it widens, you could then sell protection for the same amount and you could lock in a profit. And similarly, if you sell protection, you could be speculating on the narrowing of the credit spread. So there are both genuine hedging motives and there are speculative motives. And
Is there some statistics how many percentage are naked?
90, it's probably these days 99%. Yeah, I mean, the market is huge. And those who use it as genuine protection, I think, are a small fraction. I wouldn't like to say, you might know.
If that were not allowed, being without insurable interest, would the market still be liquid?
I think it would be a lot less liquid if you were forced to have insurable interest. So it sounds like insurance, and that's what makes it not insurance. There's no requirement for a protection buyer to actually have the bond. No requirement of insurable interest, so it is like insuring someone else's house, in effect, which of course is you can't do in insurance. Okay, so from now on we think about how we model credit risk, how we model default risk. And I just want to identify we come back to the products later. And I just want to identify two philosophies. One is the rating or scoring philosophy. That is, you collect empirical data about the payment records of obligors, and you score them based on their past behavior. Now, whether it's rating or scoring largely depends on whether we're talking about big companies with debt traded on markets or small companies whose debt is not traded on markets. So obviously the rating agencies fulfill the role of rating debt on large companies, But in retail credit risk, if it's you or I who's borrowing the money, we are typically scored using a scorecard. So in retail banking, there is a huge industry in credit scoring, in building scorecards that will assign me a credit score. And of course, you can look up your own credit score based on my repayment history and other characteristics of myself. So this is very much a statistical thing. This is very statistical, using empirical data to measure credit quality, expressing credit quality on often on a categorical scale, AAA, AA, A, but in retail banking, a credit score is usually a numerical score. Now, the other sort of philosophy for determining credit risk is an interesting one, and this is using markets to infer credit risk or to try and gain information about credit risk. So for obligors whose equity is traded on financial markets, prices are often used to infer the market's view of the credit risk of a company. And this is where the firm value models come in. This is where the structural models come in. And this is the thing that I want to explain before the break. And so I think we will move fairly rapidly through this section. Rating and scoring, there are a few slides about this. I think probably this is relatively straightforward. You're well aware of the role of the rating agencies, and you may know something about the use of scorecards in retail credit risk. Ratings are often used as a primary measure of credit risk, and many people model ratings and rating migrations. And in the book, we have a section on models for rating migrations, Markov chain models, both in discrete time and continuous time. And there's also one or two nice R scripts in the repository fitting Markov models in discrete time and continuous time to rating migration data. So I think that I will pass through these few slides relatively quickly. You've probably seen such things as rating migration matrices before. So this is an annual rating migration matrix that I got from Moody's, which gives you basically, you could effectively take them as probabilities of moving from one particular rating, this is the Moody's system, to another particular rating in the course of a year. 87% of companies, AAA companies, remain in AAA, others move into other categories. Some have their rating withdrawn, and so this isn't, we have to use this kind of data, we have to deal with the withdrawn ratings as well. Usually we would correct these figures to account for rating withdrawals. But this kind of information can be used to build a model of how companies move among ratings.
How robust is this matrix and the defaults? I mean, was it very different before the financial crisis, or has it remained, I mean, these probabilities?
Well, the rating agencies claim that they rate through the credit cycle, so that they take a long view right through the cycle. And so a rating should be viewed as a somewhat relative measure rather than an absolute measure. So a company that is A-rated now and a company that's A-rated during the crisis, that should be the same company. It's not just the fact that the rating has a direct relationship to default probability at a particular point in time.
So they rather change the default probabilities rather than the rating?
Yes.
The rating.
Yes, I would say. But the evidence in the data is they have difficulty doing that. So they should be through the cycle measures. It shouldn't just be the case that all the companies are downgraded when we move into a recession and they're upgraded when we come out of a recession. But when you analyze the data statistically, there's some evidence that they have difficulty doing that.
Is this paper drawn from statistics or just from intuition?
This is drawn from statistics. So Moody's have a big database, which they've collected over the years. So every year they will have a cohort of companies of different ratings, and they will simply count the defaults, and they'll count the rating transitions. So these are empirical migration rates. In fact, they have quite rich data, and if we'd had a little bit longer, I could have shown you the form of a typical data set where you see for each company, it maybe starts in one rating, and on a particular date, it's re-rated, it's upgraded, it's downgraded, then it has a new rating for a while, and then maybe it's re-rated again, and then perhaps it defaults. And so detailed information on the time that companies spend in ratings, from that you can estimate matrices of transition probabilities. Usually, the Markov assumption is made. So it's assumed that whatever rating you have now, that determines your migration and default risk. And the history of how you got to that rating, whether you've just newly been downgraded or whether you've held the rating A for the last 10 years, that shouldn't matter. In a Markov model, of course, it should only be the current state which determines your default risk. Again, the evidence is that that's not the case, that there is momentum, that the company that was downgraded last week to A is more likely to be downgraded again than the company that was A has been A for the last 10 years.
Probably the ratings themselves, they very much depend on a lot of extra information. Rating agencies, company check. It was one of the major warnings we gave in an academic view on Basel II, the issue of the rating agencies' ratings. Very broad issue.
Yeah. Yeah. Okay. So for insurance companies that invest in Yeah, I think, yes, rating companies is perhaps not so problematic, but still, there is a huge amount of judgment in a rating. Ultimately, it's a committee in a room that decides, do we downgrade this month or do we wait another month and see what happens? So for that reason, I mean, ratings are not universally popular, but in the insurance industry where you invest in investment-grade bonds, the ratings are often the primary measure you would use of credit quality. And in economic scenario generators, quite often what is modeled is transitions of bonds around a rating system. The one I mentioned yesterday, the Moody's, again, their economic scenario generator is based on generating transitions of bond portfolios around a rating system. The statistics of using historical data to get transition matrices I will omit, but as I've said, there's a really nice script which shows how you fit a continuous time Markov chain in the repository. And instead I'll go on to 10.3, which is sort of essential in the world of credit risk, the structural or the firm value model. There are a couple of modeling philosophies. So I mentioned a couple of measurement philosophies using ratings and using information from prices. There are a couple of modeling philosophies. There are the structural models, otherwise known as firm value models, and there are the reduced form models. So 10.3 is about structural models, and the remaining sections of the chapter will be about reduced form models, and you'll see why they're reduced form when I hand over at that point to Rudiger. Structural models attempt to
we're now in the world of what you were calling the market view.
Yeah, we're going into the market view. We're going into ways of measuring default risk using market information. And to do that, we need models, and the structural models are our first attempt. And in fact, we will only do the model of Merton, which is the progenitor, the first of these kinds of models, and the easiest to understand. So the firm finances itself very simply through equity and debt. So we have a firm that issues shares to finance itself, and it issues debt. But the debt is assumed to have a really simple form. So the debt consists of a single zero coupon bond issue with a fixed face value and a fixed maturity. So just one bond issue. You could say, what, a single zero coupon bond issue, and the nominal of that issue is B, and the maturity is time capital T. Now, at any time small t, up to the maturity of the debt, we will write the value of the equity as S, if you like S for stock, and we will write the value of the debt as B, B for bond. And so the value of the firm will simply consist of the value of its equity plus the value of its debt, ST plus BT. And so for Merton's firm, we can begin to think about what would default look like. What would default look like for this firm? Well, the obligors are the bondholders here. The obligors are the bondholders. They are owed a repayment at time capital T. They must get their principal back at time capital T. So we look at what happens at time capital T. There are only two possible scenarios. At time capital T, the total assets of the company, which consists of the value of the share component, the value of the equity component, and the value of the debt component, if they exceed the amount that has to be repaid, the nominal of the debt, then everything is fine. The debt holders are repaid. You could think of the company simply being wound up at this point. It's a one-period model, but then, of course, it may be rolled on for a further period. So if VT exceeds B, the debt holders get B back, and the shareholders are also happy. They get something. They get the residual value, and the bigger this is, the happier they are. So there's no default. But if VT is less than B, there's a problem. The firm can't meet its financial obligations. The shareholders, well, they're wiped out, and they walk away. They exercise limited liability. The bondholders get any residual value in the firm, and here are the shareholders who get nothing. And so when Merton wrote down this simple model, obviously he saw immediately the option, the contingent claim analogy. He saw that what the equity holders get at maturity is the positive part of VT minus B, and what the bondholders get is B minus the positive part of B minus VT. So he saw that these looked like contingent claims. He saw that this one looked like the value of a call option, except it's a little bit odd, because it's a claim on the total assets of the firm. VT is the value of the total assets of the firm, and the strike is the face value of the debt. So the value of equity, it's like the payoff of European call option on the assets of the firm with exercise equal to B. And this is like the value of the debt where you have the nominal value and you have a short put option, a short European put option. And so because Merton was involved in the Black-Scholes Merton model, he began to think about how he could value the equity and the debt in this context. He probably also looked at it and saw that it made some kind of economic sense in that it explained certain conflicts of interest, so between shareholders and bondholders. Shareholders are a bit more gung-ho. They're quite interested in the firm taking on risky projects because that potentially increases the value of their option. So they like volatility, whereas the bondholders don't like volatility. They have a short position and they would like to see volatility reduced. So he probably looked at this analogy from various sides and saw that it made some kind of sense to him. And then he applied the model that he'd been working on for valuing contingent claims on stocks, and that is geometric Brownian motion. So he decided that he would model the assets of the firm, because he's going to value contingent claims on the assets of the firm. He decided to model them through geometric Brownian motion, and I've written down the diffusion model here, with two parameters, the drift of the assets of the firm, they may drift up, they may drift down, and the volatility of the assets of the firm. And then I've also written down the solution to the stochastic differential equation. So at time capital T, the value of the assets of the firm in this model would take this form here. So we'd have a term here which was an increment of a Brownian motion or a Wiener process. So this WT here would be a normal variable, mean 0, variance T. And this formula would give the value of the firm. So in the geometric Brownian motion, the value of the firm at the time at which it is wound up, at which the bondholders are repaid, has a log normal distribution. This is a log normal distribution, the exponential of a normal. Everything here is just parameter. Everything else is just parameters. V0 is some starting value. And we're going to look at this with R, incidentally, in a second. Or if you like, the log assets are normal. And in this model, the default probability is really easy. If this is normal, the default probability must be a normal probability in some sense. It's the probability that the bondholders, that the assets do not exceed the nominal of the bond, or that the log assets do not exceed the log nominal of the bond. This is normal, so this is a normal probability. And once again, I'm imagining that I've never spoken to him. At this point, he stood back and he looked at it and he asked himself, does this behave in a way that would make sense? And he saw that it does, because the default probability increases in the debt level. The more debt, the larger the default probability. It increases in the volatility of the assets. That would lead so it's increasing in the asset volatility here. But it's decreasing in your initial assets, and it's decreasing in the drift. So assuming that these drift up. So mu v is positive. Right, let's actually make these pictures, because they are instructive, and talk about them. So okay, so if you want to run this script, it's called Merton Model, mertonmodel.r, and you need two packages. You need QRM tools, because QRM tools has a quick function for computing option values in the Black-Scholes model. And you need SDE. So SDE is a package that was written by, I just forget who wrote it, but it accompanies a textbook. We could find it in the documentation. It accompanies a textbook, Simulation and Inference for SDEs with R examples, 2008. And we're going to use that to generate Merton's model and just learn a little bit about how it works. So let's assume that these are the parameters I set up. So I'll talk through them one by one. The initial value of the assets of the firm is 1. So let's say 1,100,000, something like this. The process which describes the real-world evolution of the assets, so under a real-world probability measure, the drift is 0.03 per annum. So there's a sort of 3% growth in log assets, you could say. 3% annual growth in log assets. The volatility is 25% of the assets. We'll fix interest rates to be 2%. And the value of the debt that has to be repaid is 0.85, 850,000, whatever. And it has to be paid in 1 year. It's Merton's model, and we will use an Euler scheme and just generate some paths of this process. We'll generate 50 paths, and I'll just sort of run through them. So in this library, SDE, there's a GBM here. GBM, Geometric Brownian Motion, and I've chosen 50 paths, so I generate 50 paths, and then we look at them. You can see a matrix here which has 50 columns and 6 lines. It always starts at 1 million, and then you see the Euler discretization, the evolution of the SDE. Sometimes the assets go up, sometimes the assets go down, etc. And so that's one path, and there are many paths. Okay, so starting at 1 million, there are many paths. And this is 1 year later. So this is the evolution of the firm under Merton's model. And certain of those paths are default paths. Beg your pardon. Okay, we start at, yeah, certain of those paths are default paths. Any path which doesn't exceed 85 or 0.85, remember that was the face value of the debt. Any path that doesn't exceed that is a default path. Any path that does is a non-default path. So the probability of default, which we have an expression for, is the probability of a path which ends up down here, obviously. And one nice thing we could perhaps do, we could just lay the density on top, and then we'll just sort of see how that looks. So everything can be computed. Turn your heads through 90 degrees. Turn your heads through 90 degrees, and you have a log normal distribution sitting on this axis here. You have a log normal distribution. Imagine the total area under this is 1, and so the default probability is this area here.
What happens when a path goes below 0.8?
In Merton's model, it absolutely doesn't matter. So a path that goes like this and then this is not a default path. Other people came along after Merton, and they did first passage time models, and they said a path which goes below some threshold, maybe not this threshold, but maybe an even lower one, would be a default path.
We have, of course, a big problem also in solvency in general. You do a half-year or yearly view.
Yeah, exactly.
And of course, you measure the end of that period. What happens in between, I'm not saying it's not important. Dynamic risk management is a very difficult issue.
European options are easier than American options.
Right. Now, let's take two paths, one which is a default path. So example of a default path, as you see here. We're going to generate one example of a default path and then one example of a non-default path, and then talk about what we can learn from them. So I pick a seed that I know will work, and here is a path. It ends up below 0.85. And let me add a green line to start with, and let's go back to the slides and talk about, just jump over the paths at the moment. We'll talk about pricing, then come back to the two pictures. So Merton is going to use the machinery of the Black-Scholes model to value the two contingent claims on the assets of the firm. And so in order to apply the Black-Scholes model, he has to invoke the Black-Scholes assumptions. So there is a deterministic and fixed risk-free rate. And some less realistic things here. The asset value process is independent of the debt level. That's kind of exogenously imposed. And moreover, the assets are traded on a market with no frictions. 3 is sort of clearly untrue. The total value of the assets of firms is not traded on markets. The total value of the assets of a firm turns over only very rarely. When a firm is bought and sold, which happens very rarely, you get one observation of what the total value of the assets might be. What is traded continually on a market for large firms, like say Nestle or something, is the stock. So the ST is traded on a market, the stock, and perhaps a part of the debt. A part of the debt is traded. So these are assumptions that are made in order to make progress and simply apply the Black-Scholes formula. Equity is a call option on the assets of the firm. Therefore, the value of equity at some time t should be given by the Black-Scholes call formula. So we'll just call this CBS, call Black-Scholes. It will depend on time, it will depend on the underlying, and it will depend on various parameters, volatility of the assets, interest rate, time to repayment of the debt, in our case 1, and this nominal value of the debt, in our case 85% of V0. So you get the Black-Scholes formula, it has certain arguments. So that should be the value of the debt, and then the value of the equity. The value of the debt will be given in the following way. So we need to recall some notation from yesterday, some bond pricing notation. So if you have a default-free zero coupon bond with maturity T, yesterday we said we would write PTT. I will write here P0 for default-free. So P0 will be for default-free. And so this is under a continuous model of interest rates. We have here the value of a zero coupon bond. Now, you saw before that the debt payoff Perhaps we just have to go back to that really briefly. You saw it consisted of two parts. There is the nominal and there is the short put option. So those two parts have to be valued. And that's those, beg your pardon, that's those two terms here. So that's how we value the nominal. We just discount it with this zero coupon bond price. It's simply discounted. And then we have the short put option. So PBS for the Black-Scholes put option. And we can work on that formula a little bit, and we get this for the value of the debt. So in the pictures, we could add this. We could add the value of the debt, and we will add this as a red curve. And the green curve that I just put in, the green curve is the value of default-free debt. So just the first term here. If the debt were non-defaultable, so if the debt were non-defaultable, it would be valued simply in this way. But it is worth less. So we take something away. Because it's defaultable debt, it is valued at a lower level. And so, beg your pardon. So that is the value of non-defaultable debt, the green line. It goes up to 0.85. Like this, it's going up. It's an exponential curve. And then we add the value of the defaultable debt. So what happens here? So red is the value of defaultable debt. This is the total assets of the firm. So the difference between the black line and the red line is the value of equity. So this part is from the red line to the base, down here, because that's not zero. From the red line to the base is the value of the debt. And from the red line to the black line is the value of the equity. So things begin okay. The value of the debt is less than the value of default-free debt, but then they take a turn for the worse. Merton's firm heads into difficult territory. The value of the debt reduces, because at this point we're already starting to think this could be a default path. And you see what happens here. The equity value just gets smaller. It looks like there's a recovery here. And so the value of the equity increases a little bit, but then the value of the assets dive down. Ultimately, the equity is wiped out. Ultimately, the value of the equity goes to zero. The red line becomes the black line, so the bondholders get the residual assets. That's a default path. And then, of course, the opposite kind of scenario. Okay, this is a nice non-default path. Here's the value of default-free debt, and here is the value of defaultable debt. So you see what happens in this one. Things go okay for a while. It looks like the previous one. Then things go really badly, and the value of the debt reduces, and the value of the equity is very small here. Yeah, you perhaps wouldn't invest at this point. Buy shares, the value is very small. But then a recovery takes place up here. And by the time we get to about here, because geometric Brownian motions have continuous paths, and we're starting to think it's very unlikely that it's going to end up down here, it can't jump to default, then things are looking quite good, both for the bondholders and the equity holders. The value of the equity, this difference is significant, and the value of the defaultable debt climbs up to be equal to the value of the default-free debt. So that's how Merton's model works, with two paths.
Excuse me, how much to show that? I mean, could you imagine a scenario where sometime time t less than 1, actually the value of, I mean, intuitively the value of S would be less than B, but then it recovers. But that's not, that will not happen in that moment.
Sorry? So is that not, so maybe you have to say it again, Frank. So V,
Stupid question. Sorry,
a legend would be nice, but this is all, black is always the assets, red is always the value of the debt, and the difference is always the value of equity.
Question
Withdrawn, okay. I keep going the wrong way. Right, so we've talked about those two formulas. Pricing debt, a couple of things that we can look at that are implications of what we've seen. We have generated paths under the real world measure. Of course, in the Black-Scholes theory under the risk-neutral measure, the value process follows this SDE. We have this SDE here, where instead of mu v, we have the interest rate R. We can also write down a risk-neutral default probability. So this is the same expression as before. The same expression as before, except that there's an R instead of a mu v. And we'll call this one Q, the risk-neutral, and we'll call the previous one P, the actual physical probability of default. And in this model, they have a relationship. Q and P are related in this way. They would be the same thing were it not for this term. Were it not for this term, which is a sort of intuitive ratio, it's the growth rate of the log assets minus the risk-free rate divided by the volatility of the assets. And it's a sort of sharp ratio, except for the firm's assets rather than for the firm's share price. So in a sense, it's a sort of measure of the risk premium earned by the assets of the firm. And we put this one in because it's a sort of little rule of thumb or simple formula that is sometimes used by practitioners to go from the world of P to the world of Q. So if you want, or vice versa, probably typically from P to Q, if you can get an estimate of the Sharpe ratio of the firm's assets. Now, given that it's only the equity that's traded, you might have to settle for an estimate of the Sharpe ratio.
Normally you want it the other way around. Q default probabilities are easy to get sometimes. P ones are the difficult ones.
Yeah, probably actually, yeah. So anyway, this bit you would have to get from equity data. Either you go from P to Q or Q to P. As Rudiger has just said, Q measures you can get from prices, and so going in this direction is about inferring real-world probabilities of default from information that can be extracted from prices. So if we can, in a pricing model, if we can infer what Q is for a pricing model, this will allow us to go to P. If we fill in a number here, that's the idea. And then the other thing is we can look at the credit spreads of the bonds in Merton's model. So the bondholders, they have a defaultable bond. So their bond offers a spread over a default-free bond. So that's related to the difference between the green line and the red line. You had the green line was default-free debt, the red line was defaultable debt, and that difference that is related to the extra compensation that Merton's bondholders require for buying defaultable debt. So that's related to the spread. And we can get a formula for the spread. So it measures the difference between the yield of the default-free zero-coupon bond, the gilt or the treasury or whatever, and the defaultable bond issued by the firm. So whereas we called the other one P0, we shall call this one P1. And what would it be? Well, the total bond issue has nominal B. The total bond issue is nominal B. So P1TT, we would have to scale the value of the debt by B. We'd simply have to divide by B. And this would give us the price of the bond that pays 1. So as Rudiger explained yesterday, in this notation, this is the bond that pays 1. So we scale B, we can get an actual formula for this. The spread, it's a difference in yields. So one yield minus another yield. So on the left-hand side, the yield. I'll just keep.
Yeah, okay.
Yeah. And you get a formula. And one person had a look at it to check whether it behaved in a sensible way. It actually depends on only 3 things. If we fix the times, in fact, on only 2 things. If we fix the times, it depends on sigma v, that's a key parameter, and it depends on a simple ratio, b discounted, so we discount the nominal debt and we divide by the total value of the assets. This is a kind of measure of leverage or indebtedness, and so this makes sense. If sigma v increases, the spread increases, more compensation. And if this indebtedness or leverage increases, the spread increases. So more compensation is required. And this seemed to make sense, but when you actually plot the spreads in Merton's model, they are not realistic. They're not realistic, So for example, here's the spread against time to maturity. 1 year, 2 years, 3 years, 4 years. The parameters are as we have them. And then for short times to maturity, quarter year, third of a year, this spread is essentially zero, which is unrealistic. In reality, market spreads would be larger. And this relates to the fact that by the time you get near to the boundary, you pretty much know whether you're going to end up in default or not. You can't jump to default, and you can only be in default if you're under the line at the far end. So there are many deficiencies of the model. It's clearly not particularly realistic, and a whole industry began after Merton adding more realistic features, putting jumps into the stochastic process, allowing default at intermediate times, etc. And you'll find some references in the book. But what we have here is a way of going, well, if I just go back to one formula to conclude, and then Rüdiger needs to start. One formula to conclude. On the left-hand side, we have equity. On the right-hand side, we have the value of the assets. If we want to get a default probability, let's go back to the default probability. We would need to evaluate this. If we wanted a real-world default probability, we would need to evaluate this. And we would need to know certain things. For an actual firm, we'd need to know what is sigma v, what is mu v, we need to know what is the value of the assets. These things, sigma v and v0, are important but difficult to determine. Mu v is probably not so important. So to evaluate this, we would need to get information somewhere. And if we could use stock prices and this formula here to sort of reverse engineer the value of the assets, we could get a measure of default risk applied from stock prices. And this is what happened next. People took Merton's model, Mr. Wassercheck, Mr. Kielhofer, Mr. V, they took this model and stock prices. They had a method for reverse engineering information they needed to compute default probabilities. We go into that in the book. We won't go into this afternoon. Instead, we'll go on to the models that are more commonly used for bond pricing. So you probably wouldn't use Merton's model to really price a bond. Instead, you'd probably use a reduced form model. And I'm about to hand over the baton to Rüdiger, who's going to do the remainder of this. Make a start before coffee, I think. And
yeah. Which one is it? It's this one, I think. No? Ah, that's the trick. Good. Okay, so as Alex said, in the introduction to credit risk, there are basically two types of modeling philosophies or approaches for credit risk. On the one hand, the firm value structural models, where Merton's model is really the simplest example, where you start from the economic thinking that default has something to do with insolvency. It's not exactly the same, but closely related. So you start modeling the assets of the firm and some default barrier and model default in that way. Now, you can say that is a bit too complicated in some sense. You're modeling an awful lot, given that for many pricing applications, all you really need is something like the distribution of the default time. And on the other hand, it's also so that the story that default and insolvency is exactly the same. So insolvency means really that the value of the assets is lower than the value of the liabilities, but there are firms that are insolvent and not default because somehow they are allowed to continue, and there are firms that are default even if they are solvent because they are in a have short-term cash problems and don't find anybody to lend to them. And so there is this alternative idea of using the simpler reduced form models where you model directly the default time and where its distribution, of course, can depend on economic characteristics of the firm or also, of course, of the sovereign you are interested in. So we will always talk here about the defaultable firm being, the defaultable entity being a firm, but all of what we're saying, in particular in the reduced form approach, applies just as well to countries. I mean, in the old days, if you were not just investing in Argentinian or Mexican bonds or so, you would consider the stuff essentially default free. As so many things, this has changed. So the whole reduced form methodology really does apply to sovereign bonds just as well. To which bonds? What is that? Yeah, I know what GDP is, but GDP bonds, exactly, they are.
Yeah, they are bonds where they pay them based on the GDP.
Where the payment depends on the GDP?
Interest rates, they have like a mechanism that they pay based on share of.
It's like inflation linked.
Oh, yeah, like inflation linked. Okay, then I guess for a GDP bond, of course, you would probably more use an approach which is closer to this firm value approach, because there you have to model well, for a GDP bond, you would probably have to model the stochastic evolution of GDP if you wanted to price it. So there, you would be more inclined to having a firm value type model where you have the GDP, and then you would perhaps assume that the tax revenue of the sovereign is somehow related to this GDP, and if this is too low, then you have a default, something like that. So you would be more in the structural modeling philosophy for these things. Okay, before we be getting too special here, let's stick to these models. Now, hazard rate models, these are the simplest models where we assume that the hazard rate is deterministic. They should be familiar to all of you, because basically with a slight change of terminology, you could call them also like life insurance products, more or less. I mean, tau is here a default time of a company. It could essentially also be mathematically the death of a person or something like that. Good hazard rate models are the simplest reduced form models. They are the building block for more complicated ones. The distribution, that's the specific point of the default time, is directly specified by a so-called hazard function. We do not model the mechanism by which default occurs. We work on some probability space, and we have considered a random default time tau. So to start off, I will introduce a few mathematical notations around these hazard times before we apply them. So random time is just a random variable with positive values. The distribution function is f. The survival function is going to be f bar. Bar always survival function, which is 1 minus f. In the context of these models, it's very often more natural to work with survival functions because it saves you a couple of 1 minus terms in all formulas. So the probability that tau is bigger than t, we assume that at the initial date the firm is still alive. And we assume here in these models that there is no a priori given upper limit to the lifetime of the company.
Is there some additional assumption on what if I think that 50% probability that the company will not default forever? Can that be included?
That can be included. Then it would simply mean that this probability function will for every t be smaller than 0.5 and sort of have.
So that would be
Mathematically you could include in these models. It makes really sense to consider it really as a probability distribution on 0, infinity included, and tau equals infinity simply means that it's never happening.
Okay, all right.
So then
So it's not a technical problem.
it's not a technical problem.
All right.
You could choose a defective distribution function.
Yeah, or you do that. Okay, then for some of the dynamic modeling, it's useful to have a piece of notation, the so-called default indicate. It comes, yeah. Good. The so-called, and then I should know by now. No, that was too much.
You need to solve an equation to get the right.
Yeah, yeah. An algorithm, Marius, somehow slowly getting there. Good, I just want some picture. The default indicator process, this is time. If we assume that the default time happens here, here is 1, then there's a process which is 0 here and jumps to 1 directly at the default time. That is the indicator that tau is smaller or equal to t. There is also a survival indicator, which is 1 minus that. This is 1 here and then 0 from here onward. This will appear sometimes in our formulas. Good. Just as a piece of notation. And then, oh, sorry, this is what I need. The cumulative hazard and hazard function. Well, normally, I guess all of you know this from life insurance modeling. These distribution functions are typically not written down directly, but we typically parameterize them in terms of hazard rates or hazard functions. And I'm going to introduce these objects now. Gamma of t, which is minus the log of the survivor function, is the cumulative hazard function. And if X is absolutely continuous and has a density, which is the case for all the examples considered in this context, the function gamma, which is the ratio of the density and the survivor function, or equivalently minus the derivative of the log of the survivor function, is called the hazard function, and the hazard or hazard rate function. And that is the typical object of interest in which we parameterize these models typically. And the reason is on these 2 bullet points. First of all, you see that you can write the survivor function as x power minus integral from 0 to t gamma of s ds. So in the simplest case of an exponential distribution, this hazard rate would be just constant, and you get x power minus lambda t. But you can, of course, do something more sophisticated, and you can describe basically every function here, or distribution function for such a lifetime in terms of its hazard rate. And you have a nice economic interpretation. You can show that, well, let's look at this expression here. First, without the limit, just the probability that default happens in the next instant. So we're standing now at time t. We are looking for the probability that default happens in the time t plus h, given that we're still alive at time t. That's the probability which is written here. Of course, if h is small, this probability will turn to 0. But if we divide it by the length of the time interval, we blow it up again. And so that's why this is sort of the instantaneous chance of default, what is written here. And it's clear basically from the definition, well, this probability here can, using elementary condition expectation, be written as f of t plus h minus f of t. And then we divide it by h, and we get, of course, and divide it by f bar of t, sorry, and the whole expression is equal to the hazard rate. So the hazard rate is sort of the instantaneous chance of default, given that we've survived. So far, I already mentioned for the exponential distribution, the hazard rate is constant and equal to the parameter of the exponential distribution. If you take a 2-parameter example like the Weibull distribution, that a distribution function is y minus x power minus lambda t to the power alpha for lambda and alpha bigger than 0. Of course, for alpha equals 1, you have the exponential distribution as a special case. And if you just compute, this is the density here, and then the hazard rate is lambda alpha t to the power of alpha minus 1. Now it's interesting to see if this hazard rate is decreasing or increasing in time. So that means that if you've been waiting, the interesting bit maybe about the exponential distribution is that it's constant. Or the standard joke of Freddy Del Barn used to be that's the mother-in-law distribution, to be slightly politically incorrect. A constant hazard rate means, in the context of the mother-in-law problem, no matter if your mother-in-law has been talking to you for 2 hours, the probability that she will continue to do so for the next 2 hours is unchanged. I never met his mother-in-law, maybe Paul or Hans have. This is one extreme case. Then the other one is that you have an increasing hazard rate. So if you've been waiting longer, the chance that something happens increases. This is overall the case. It's not throughout the case for human lifetimes, for instance, at least beyond. There are certain small bits, I think, in the curve where it's non-monetized, but typically the chance for an 80-year-old person to die in the next year is higher than the chance for a 20-year-old person. And the opposite thing is that the intensity is in fact decreasing. Well, this may be, for instance, the case when you're waiting for a train in whatever, Germany. They have had enough strikes also, say, for a train in Germany. If you're waiting a little bit, you hope that it may come. If you've been waiting for 2 hours and it's still not coming, then maybe it is cancelled and it will sort of never come. That would be a typical case of a decreasing hazard rate. Here with this Weibull distribution, you can model increasing or decreasing. You can have more sophisticated examples where you can have both things. Good. That's just to have this notation clear. I will be brief here, it's more for notation. Well, we will do coffee break now, I think. And we will continue with this afterwards. Good. Welcome back. The good news definitely is it's at most an hour to go, so there is an upper limit for once. And a few words about the next slide, filtrations. Of course, we want to do some pricing of bonds or CDS, and in principle, if we want to consider pricing models and financial pricing using risk-neutral pricing, hedging, and so on, we need dynamic models where we really model how things evolve over time. And if we like the Black-Scholes, like this asset value path Alex showed to you before the break, and if we do that, then in principle we also have to model the fact that the information set of investors and the things they can use in forming trading strategies or making decisions gets larger as time goes on. And mathematically, this is done via the concept of filtrations. They model information available to investors over time. Formally, a filtration is an increasing family of sub-sigma bars. So if T is smaller than S, then FT is smaller than FS, because in these models, people don't forget. That is, the amount of information that is available is always only increasing. And the fact that the set is measurable, FT measurable, means that at, say, a set A, that at time T, an observer of the system can decide if that event has happened or not. That's the idea. So in this theory, sigma fields and filtrations are not just a technical necessity. You need to be able to do integration and define expected values or probabilities in a consistent way. They are really important tools to model information, and it is quite frequent to have several informations around at the same time. Paul mentioned, I think, insider trading models in this context. There can be also other such things. Now, I don't want to push this too far. This is not a mathematical finance workshop here. But a little bit we need, if only to make the notation of the slides understandable. In these very simple models, reduced form models, where there is sort of not much economics going on, there is not so much economic quantities being modeled, and so we assume the only observable quantity is the default associated with respect to tau. the default indicator. So basically that means at time t we know only, well, we know if default has happened or not, and if it has happened, we know when it has happened. That's sort of the simplest thing, so we know the history of the default indicator up to the time, and we call the corresponding filtration HT. Later on today, when we consider models with stochastic hazard rates, there will be more economic information, and there might be things like stochastic interest rates and some economic state variables that model maybe GDP or other economic quantities around, and then we will need bigger filtrations for the moment. Now, the next result is useful because it tells us how to compute conditional expectations with respect to the simple filtration. What this means is that if we want to compute the conditional expectation, suppose that the firm is still alive and we want to compute the conditional expectation of some event with respect to the default, given the default information, default history up to that time point, then okay, this is 0 if default has already happened, and otherwise what we have to do is we have to take sort of the ordinary expectation of the product of the default indicator and the thing we want to price normalized by the survival probability, and this result can be used for conditional survival probabilities. For instance, the probability that tau bigger than t, given the default history up to time t is, well, if default has happened already, this probability is 0. That's why we have this indicator here. Sorry, I didn't switch for some reason. That's why we have this indicator here. And the probability is the indicator that tau is bigger than t times this integral from small t to capital T over the hazard rate. This is a formula we will sometimes use. The next slide about the martingale property of the jump indicator process we can skip. This is not really needed for us here. Okay, so that's sort of the mathematical tools to understand the hazard rate models. And now we come to some financial tools. We will have a very quick look at risk-neutral pricing to refresh your memories, and because it is important to distinguish it from sort of actuarial valuation principles. And good. So risk-neutral pricing means that in order to compute the price of a quantity, you take the expected discounted value of the payoff. But you're not doing this with respect to the physical measure. You're doing this with respect to some artificial measure Q, the risk-neutral pricing or equivalent martingale measure. And this has the property that it turns the discounted prices of all traded securities into fair bets or martingales. And for those of you who have not seen this before, I think most of you have. Oh, this is too much. Well, I have a very simple example here. It's the example of a corporate bond or defaultable bond, and this bond has a current price of 0.941, and there are two possibilities. Say in 1 year, either the bond, the underlying firm is not defaulting, then we get 1 in return, or the firm is defaulting, and then we assume in this case there is a recovery payment of 0.6, so a recovery rate of 60%. The default probability, the historical default probability, we assume we know that is 1%. And the interest rate is 5%. So the payoff would be 1 minus P, 1 with a probability of 99% and 0.6 with a probability of 1%. And the first thing we could do, you find this in Chapter 2, is to compute the expected discounted payoff of the bond. This would be this expression here, but with the real default probability in here. And if you do that, you end up at something that is slightly higher than the assumed price of the bond. Now, what is in this context an equivalent martingale measure? Well, this is a very fancy name for a one-period model with two states in the world. So all we need here is a risk-neutral default probability. A probability of the default, which is a fictitious thing, it's just a number, a probability, and if you use this artificial probability, we can explain the current price, namely the current price of the bond is the expected discounted value of its future payoff with respect to this artificial probability. This leads us to this equation here. The current price, which is 0.941, should be equal to the discounted value. This is an old example. Interest rate is 5%. So we do discount with 1.05, and we take the expected payoff, which is Q times 0.6 plus 1 minus Q times 1. And if you solve this equation, this is done in the book, but I think you believe me, then you get a risk-neutral default probability of Q equal to 3%. Of course, the example has been re-engineered, and I assumed this default probability, and then I got this number, but never mind. Now, what are the two important things to take away, sort of, if you have problems keeping these two concepts apart? The first one, it is different from the historical default probability. That is typical, and the typical situation is also, as indicated in this example, the risk-neutral default probability tends to be higher than historical default probability. Why? This sort of embodies risk aversion on the part of bond investors. Because if it was equal, if Q were equal to P, then this would mean that the expected payoff on a defaultable and on a default-free bond were the same. And then most investors, I guess also you would say, well, if in both investments I make the same expected return, then why should I take the additional default risk? I'm not a gambler, I would just buy the default-free bond. So investors require some sort of a premium for taking on the default risk, so a slightly higher expected return, and that's why typically the risk-neutral default probability tends to be higher. Good. The other thing, well, in fact, there are even three messages to take away. The other thing is, how did we find this Q? We didn't do any statistics. We just solved an equation. We looked at current market prices. So risk-neutral probabilities are those probabilities that somehow explain current market prices under some structural conditions, of course, on the underlying model. So there is no statistics here. To determine the historical default probability, we might have to do some statistics, look at firms with similar characteristics and check their default rate in the past or something like that. Here we do something, in fact, simpler. And so that's P versus Q. And also we had, I think, in one of the first lectures in this workshop, a little bit of a discussion, what is estimation and what is calibration? I think that was your question, yeah? Calibration, so the terminology as I use it and as I think it is very often being used as in literature is, if you do something like that, where you try to reverse engineer model parameters from observed prices, you would talk of calibration, and if you do real statistics, you would talk about estimation. I think that's sort of the standard terminology, but these things are, well, both words are not always very carefully used. Of course, calibration, yeah, and historical volatility is estimation. Exactly. So actuaries know this also. They will talk about market consistent valuation as a special case of this. Good. Another question is, of course, why should we do this? What is sort of a theoretical justification for using such a pricing principle? Then also, okay, here just computed the price of computed the risk-neutral default probability, but I might then go on and say, well, I would like to price also other derivatives which are non-traded. For instance, I could consider a very stylized default swap in this very simple model. So the very stylized default swap would be like a swap is an insurance against default. So that could be something that gives me 1 here and 0 here, and I could price such a thing. And what I would do under the risk-neutral pricing approaches, I would sort of just take this probability and I would price the default swap as expected value of the discounted payoff with respect to this Q. That is risk-neutral pricing. But why? I mean, you can come up with many pricing formulas, but there should be some justification for that. There are 2 justifications. The first one is absence of arbitrage. It is well known, and Paul's colleague Freddy Delban has devoted half of his scientific life to figuring this out in ever more mathematical detail, that whenever you have an arbitrage-free model, so whenever you have a model where there are no risk-free profit opportunities, then there should be a risk-neutral measure or an equivalent martingale measure up to some technical conditions, and the other way around, if there is a martingale, if there is such a measure, then there's no arbitrage opportunity. That's easy. And so whenever we make a model, we would want to make a model that is arbitrage-free, because a model that, even if you believe that the real world out there maybe has some arbitrage, but a pricing model with arbitrage that is a little bit like a hammer with a broken handle. If you use it, it will flow around your ears at some point. So we don't want that, and that's why we will want models where we have such a risk-neutral probability. And of course, if you price other products, this should be consistent. So if you include these other products into the set of traded securities, the model should be still arbitrage-free, and that's why we should use risk-neutral pricing. The other, maybe more convincing argument, which has the advantage that it's more convincing and the drawback that it doesn't always work, is based on hedging. In many situations here, this would be a case in point. You can reproduce the prices of traded securities by a clever portfolio, static or dynamic, and then you can say, if I can reproduce a payoff of a security with clever trading, then the amount of money I need to do this clever trading should be the fair price, and it's easily seen that the amount of money you need is exactly the expected value, expected discounted value under such a risk-neutral measure. However, in many real models, such replicating strategies do not always exist, and there is then also more than one measure. And we are in the area of incomplete markets, but that is maybe too far for this lecture. So that's a little bit this justification for risk-neutral pricing. It is quite important, and it is also important that you really keep the difference between P and Q clear in your mind, because in risk management you will very often have the problem that you need to work with both measures at the same time. We do an example for that tomorrow. Alex has a very nice R script where it comes to doing computing or doing risk management for an interest rate swap, and there we sort of need, if we want to understand sort of the risk in an interest rate swap, the risk factor is going to be the interest rate, and then we need to model the P dynamics of the interest rate to get the distribution of the value of this thing tomorrow or in 10 days. But on the other hand, to have the mapping between the value of the interest rate, say in 10 days, and the value of the swap in 10 days, we need to do some sort of risk-neutral pricing. And for that, we need the Q dynamics of the interest rate. We need to come up with a zero bond curve or yields. So we need both of these things simultaneously, and that's why it's important to keep them apart. The last thing maybe here, what you already seen, we made this comment when we talked about the link between risk-neutral and historical default probabilities in the Merton model. Typically, this calibration is somehow easier. You have to solve an equation, maybe a complicated one with some optimization software. Still, this is easier than doing statistics and data gathering, and in a sense maybe also less subject to, well, I wouldn't say subject to error, but it's less ambiguous what the right approach is.
You can hand it over to a machine in a way.
You can handle this to a machine, exactly. And you can sort of, it's less arbitrary which method to use. And of course, if your evaluation depends on that, and you might have an inclination of using another measure where you build balance sheet, another statistical approach which makes your balance sheet look nicer and things like that. So in that sense, this is less arbitrary. And that's why there's always a temptation of trying to come up with risk-neutral default probabilities and then find a magic mapping to historical default probabilities, but unfortunately, there are approaches, but they are also very arbitrary. So that's a little bit the invariance of difficulties in life. And good. Oh, Alex, you need to help me here. Good. I've been talking too long, but I think this is, yeah, that's the one that doesn't work. Good. But I think this is always important. Now, martingale modeling, coming back to the slides. When we want to set up a pricing model for corporate bonds or for default-free bonds with stochastic interest rates, it's quite convenient to do a shortcut which is termed martingale modeling, and that is to set up the dynamics of things directly under the risk-neutral measure, and not as when you do Blake-Scholes, for instance, you start by modeling the stock price dynamics under P, and you have the drift mu, and then you have to do whatever, those of you who did the course in financial mathematics may recall, then you discover that the option price doesn't depend on this drift, and then you do some change of measure, and you need complicated Gasanov theorem and stuff, and then at the end you arrive under the stock price dynamics under the martingale measure, and then you continue to work, and from then on, the mu never appears in derivative pricing at least, and so you could ask yourself, why do I need this to begin with? I could have started straight away under Q and saved myself a lot of hassle. And not only that, if you price a stock, this is not so much of an issue, but you have one stock, and so it's difficult to model it in such a way that there is arbitrage. When you want to do interest rate modeling or also default, when you have many defaultable securities related to the firm, same firm or so, then constructing models in an arbitrage-free way is more complicated. Most obviously, this is when you do term structure modeling, because in theory, at least, you want to model the dynamics of bond prices of all maturities. In practice, there are only finitely many maturities, but this can be many bond prices, and it's maybe not reasonable to have so many risk factors in your model. Alex showed us that we need maybe 3 in his principal component analysis. And so there's really an issue of writing down a model in such a way that it's arbitrage-free. And if you start directly under martingale measure, this problem is solved. We have sort of assumed it away. Things are consistent. And for these reasons, martingale modeling has become convenient. And this is even easier if you know the value of the payoffs at maturity as for zero coupon bonds or defaultable coupon bonds. So what one does is that you directly use this risk-neutral pricing formula as, that's the right one, as the definition. You define the price of an asset via this formula. Of course, again, when you use this approach, things don't come for free. What happens is if you use this approach to set up, for instance, a model for defaultable bond prices, then you have one problem. Your model gives you a bond price, but of course you also observe one in the market, and the overall philosophy of derivative pricing is always that you do it relative to the market, so the market price is king, and you want to set up your model so that it fits to the market price you observe. And this is exactly the issue of calibration. You need then always to determine the parameters of the model, maybe of the the risk-neutral default probability, so that the value that comes out of such a pricing formula today coincides with the price you observe on the market, which is called calibration. And we want to now apply this approach to defaultable bonds and credit default swaps in the context of these simple reduced form models. Pros and cons of martingale modeling, maybe very, very briefly, only in the interest of time. The pros I already mentioned. It can be convenient. You get by definition models which are arbitrage-free. The cons, this calibration can be very complicated, and from a more methodological point of view, if you have only relatively little price information, only very few securities that are traded, that are somehow related to the things you want to price, then this market completeness issue plays a role. Then it's probably not possible to determine the Q uniquely, and then it would be more natural to do something which you do in insurance anyhow, where if you want to price something like an insurance contract, you look at the expected loss plus risk premium. But as long as you're in a quite liquid market, this is a useful thing to do. Good. Bond pricing. We consider zero coupon bonds, martingale modeling. We assume that under the pricing measure used, the default time tau is a random time with deterministic hazard rate function gamma q. The information available to investors is the default history. Interest rates and recovery rates are deterministic, not necessarily constant. They may depend on time, but they are deterministic. Percentage loss given default is delta, so in case default happens, a certain percentage of the notional is sort of lost, and that's this delta. R of t is the continuously compounded interest rate, and the price of a default-free zero coupon bond with maturity t is x plus minus integral from small t to capital T R of SDS. And if R is constant, that's of course equal to x plus minus R times capital T minus small t. That's the setup. Now, let's look at a typical corporate bond. Then there you can decompose it into two building blocks. The one, sort of the most important one, if you want, is a so-called survival claim. We assume the face value is 1, and if the underlying firm does not default, then at the maturity date, we will have a payment of 1. On the other hand, that's the first claim. The survival claim, where we say we get 1 if the firm survives, and we get 0 if the firm defaults before the maturity of the bond. However, in reality, of course, when an underlying firm defaults, typically not all is lost, but you get some recovery payment. And this we need to model as well. Let's start with a survival claim. The payoff is, of course, 1. The indicator that tau is bigger than t. And so we have the risk-neutral survival probability. The probability that tau is bigger than t, capital T, HT, is the indicator that the firm is alive at the valuation date, small t times x of minus integral from small t to capital T gamma q of SDS. That's the same formula as before. And now it will be convenient to introduce an artificial interest rate. So R is the real interest, the interest rate, that's the hazard rate, and if we sum the two, we get some sort of artificial interest rate, capital R, and if you use this piece of notation, the price of a survival claim at time t is, okay, that's the expected value under Q of the payoff discounted. That's discounting with the default free zero coupon bond. This first expression here is just the price of the default free zero coupon bond written out times the survival probability. And if you use this formula for the survival probability here, you see that the whole expression is indicated that the firm is alive at small t times the discounting expression here, x plus minus integral from small t to capital T R of SDS. Now if you look at that, that looks like the price of a default-free bond, only with another interest rate. So we see here a principle which we will see also later on in the more sophisticated models. In many models, it is possible to reduce the pricing, at least of survival claims or of defaultable zero coupon bonds, to the pricing of default-free zero coupon bonds. Of course, a defaultable zero coupon bond should be worth less because you cannot be sure that you get your money back. And this is modeled by discounting with a higher interest rate. And this higher interest rate is just the sum of the default-free interest rate and the hazard rate. So that's what we get here. To move on, we need to, that's what's written here. To move on, we need to also model the recovery payments. And there are a couple of potential recovery models in the literature. What really happens at recovery is difficult to say. But we will consider basically two models which are quite popular. And one of the two we also need for the CDSs. The first one is the so-called recovery of treasury that was proposed by Jerry and Turnbull, and mostly for convenience. The idea is the following. If default happens at tau, say we have a 1-year bond, and default happens after 6 months, then at the default time you get maybe the recovery rate is 40%, so you get 0.4 units of a now default-free bond, which has the maturity date 1 year from now, so time to maturity would then be, in my example, 6 months. The beauty of this assumption is that in this case, the payoff you get at the maturity of the bond is independent of the timing of the default. You get 1 if there was no default, and 1 minus the loss given default, so the recovery rate in case there is default. The recovery of face value, which is maybe the most realistic and the most frequently used assumption, it's slightly different. There it is assumed that you get a recovery payment of size delta, but not at the maturity of the original bond, but directly at default. In practice, you don't get it directly at default, but there is some negotiation and so on going on. But it's typically not postponed until maturity. You get it then maybe half a year later or something. And this is more realistic. It has one slight drawback. The value of this thing depends on the time of the default because there's some discounting going on. It does make a difference if the default happens very soon after the bond has been issued, and then you get your money very early, or if the default happens short before maturity and you get your money very late in this setup. The value is okay, recovery of face value. The value is the following expression of the recovery payment. You get payment of size 1 minus delta. You get it directly at tau. That's why we have a discounting here up to time tau. And you get it only if, okay, the bond has to be alive at the time when you do the valuation, and default should happen before maturity. Otherwise, you're not getting any recovery payment, but of course, instead you get just the normal payment of the bond. And we have to take the condition expectation with respect to this default history. Now there's a useful formula for that, using the fact that this is, of course, the expectation of a function of tau. Tau is here, and tau is here. And because we know the conditional survival function of tau, we know also its conditional distribution and its conditional density, and we can compute this expectation here. And you can show this is 1 minus delta, indicator that tau is bigger than capital T times the integral from small t to capital T, gamma q times minus x power minus integral from small t to s r of u du ds. So that's here the discount factor in here and this density of the default time. And that is a so-called payment at default claim, which we will also use or encounter in the pricing of CDSs. Good, that's the next thing, CDS pricing. So Alex explained to you earlier today what a CDS actually is. So let's quickly recall the payment flow. Tau is the default time, C was just the reference entity. I think that was Nestle in your case. And premium payments are due at deterministic times, typically 4 times per year. At each of the premium payment dates, a premium of size spread percentage of the notional, which is typically quoted in annualized terms. That's why this is so complicated. So if it has that the CDS spread is 2%, it means that 4 times per year you get 0.5%. That's the annualization is being paid. It's a little bit like a life insurance contract. So as soon as the insured person is dead, there are no premium payments anymore. That's the same thing here. And if tau happens before the maturity, then there is a default payment of size delta. In reality, the size of the default payment is linked to the recovery rate of bonds, but we assume for simplicity that it's constant. In some contracts, there are also so-called accrued payments, but we ignore them because they are not so important. Good, we can now price these two things. The premium leg is nothing else but a portfolio of survival claims. Each premium payment occurs at a deterministic date, and it has a deterministic size. The only thing that is random is that we have to make the premium payment only if the reference entity is still alive at that time. So it's a sequence of survival claims, and each of these survival claims we can price, and that gives us the value of the premium leg, of the premium payments. One talks of legs of such a transaction. Good. Here. That's the value of this premium payment leg. And this is easy to compute because we know the conditional, or here I'm doing it at t equals 0, so I know the survival probability. And that's the value of this premium payment legs. Suppose that at the valuation date, the firm has not yet defaulted. That's the spread. And then I have to sum overall premium payment dates in the future. And I have to sort of discount with this artificial interest rate to take into account that the premium payment is only due if there is no default. The default leg is a payment directly at tau, provided that tau is smaller than t. That is exactly what we have just computed to do the recovery payments of the bond under recovery of face value. And we get this expression here. It's the same thing as before. Good. And if you want to, now you have to remember that these contracts are typically done in such a way that they are an exchange of payments, and the contracts are designed in such a way that at the moment when the contract is being done, its value is 0. So if I want to do a CDS contract with Paul, and we want to insure each other against Alex's default, because if he's no longer here, we have to write our R code ourselves, and we need to hire somebody. Good, we have to do that, and sort of Paul wants to buy protection against the fact that Alex, whatever, defaults, and is not, and I'm willing to sell that. Yeah, then Alex has a firm. Alex's firm defaults. How is it called? QR Analytics or something. And I want to sell it, then we have to agree. Maybe Nestle would have been better, yeah. Then we have to both agree on a spread. Of course, if Paul wants to buy protection, he wants to have his insurance premium as low as possible. I'm selling it, I want to have it as high as possible. We have to simply agree on a premium so that we're both willing to do it. And typically, there's no cash exchanging hands when we do the contract, at least not in Switzerland. And that's the fair spread of these things. Mathematically, if we want to compute the fair spread, given a pricing model, we have to solve an equation. Namely, we have to find the value of x star such that the value of the premium payment given X star and the default intensity gamma Q is equal to the value of the default payment, which is independent of the spread. Now if we go back here, the value of the premium payment for a given spread X is just linear in X. It's X times something. And so to solve this equation, we simply have to divide the value of the default payment by something which gives this formula here for the for the fair spread of the contract. Good. That's the first part, that's the pricing. In reality, the market for this credit default swaps is quite liquid. The one for swaps on Nestle is. In case of Alex, that's a little bit more complicated. And so one would do it the other way around. We would typically say we want to determine this risk-neutral default intensity gamma Q so that the spread we get from our model coincides with the spread on the market. This would be the calibration. In the simplest case, whenever we have only, it depends. For some firms, there's only a 5-year CDS outstanding. For some very big firms, you find also CDSs of other maturities like 3 years or 7 years and so on. And in the simplest case, where there's only one maturity there, it also makes sense to use also a very simple model for the risk-neutral default distribution, namely an exponential distribution which has a constant parameter. And so we would have to find a constant gamma Q bar, the risk-neutral default intensity, such that if you use this gamma Q bar, the spread that comes out of our model equals the spread we see on the market. So gamma Q has to solve this equation here. This is the value of the premium payments for the given risk-neutral spread. That's the value of the default payments for the given gamma Q. Now, if you think about it, you can also show it, but economically it's sort of clear. The value of the default payments, that increases if the default intensity or the hazard rate goes up, because if the hazard rate goes up, it's more likely that default is going to happen before the maturity, and if it happens sort of early, which means I discount less. The value of the premium payments is, of course, decreasing in the default intensity. If the default intensity is small, the value of the premium payments is quite high because it's likely that I'm going to get all of them. If the default intensity is very high, the value of the premium payments for fixed spread is low because then it's quite likely that I will not get the later payments, and so there is a unique solution. If the situation is more complicated and you have more than one CDS outstanding, you have to either use 2 or multi-parameter distribution for gamma Q for the hazard rate, or what practitioners very often do is to use piecewise constant hazard rates, and then you can do it with a backward calibration with a backward of. It's forward induction. You first calibrate the shortest, then the next, and so on. Good. That's how these things work. If you look at the numbers, you see that the implied hazard rate that fits this spread, gamma Q bar, is roughly equal to the ratio of the observed spread and the loss given default. So sort of spreads that come out of these reduced form models for short horizons, they are typically like that, and they are typically positive. That is one of the things that is different in this context than in the simple structural models like Merton, Alex talked about before the break. Okay, the last bit, pricing with stochastic hazard rates. Now, these models we've considered so far are very simple. They're enough to value a CDS or to determine risk-neutral default intensities from a CDS. But in these models, the only risk factor is default, and there is no real randomness as far as a CDS spread is concerned. As long as the underlying is not defaulted, the CDS spread evolves deterministically. And this is not enough for many things. For instance, if you use such a model, you cannot do risk management for bonds because bond prices would evolve in a deterministic manner. That's not what you want. You want a model where credit spreads are somehow dynamically and where you can have distributions and compute value at risk or something like that. You could not price options on bonds or options on CDSs because for that you need also dynamic models. So to do many interesting things, we need more complicated models where this hazard rate is itself stochastic. And the idea is to drive hazard rates by a second stochastic process. So the default mechanism has two sources of randomness. On the one hand, we have the default. On the other hand, we have the randomness in the hazard rates. And that's why these models are sometimes also called models with doubly stochastic, two types of stochastic random times. They're also known as Cox models. And I think in the context of survival analysis, they were introduced by David Cox. Good. So now, I mean, here I have to, the idea is that I will give you just a flare of the results you can obtain there for two reasons. The one is that we're running out of time. And the other one is that if you want to do everything in detail, then this would become more of a course in continuous time finance. And that's not what you've booked here. So you haven't paid for that, yeah. And in this world, in the world of finance, if you haven't paid for it, you don't get it. There is no free lunch. Except for tomorrow, of course. And as the old joke goes,
Give us a free coffee now in the last 5 minutes.
no, it's not free. You get it only if you listen to this. So you have to pay for it. Yeah, you can probably, yeah, that's interesting. Maybe tomorrow you can then auction off your remaining vouchers to students here.
No, it doesn't work. There's a stopping time on the validity of
Yeah, that's why you have to do it tomorrow in the morning. And then see how the price is going to decrease. Okay. No experimental economics here. Good. So here what we have in abstract terms, we have a slightly more complicated filtration. We need now to have some additional economic quantities like stochastic interest rates, like GDP or other variables, and they will drive the hazard rate. So the typical thing is you model some process and the hazard rate will be a function of that process so that there is some variability in bond prices and credit spreads. And in abstract terms, you simply say this process generates a filtration FT, and the FT contains all information about these economic background events except default. And then default is modeled as before by default time. We have the default indicator, we have the default history, and then we put both things together. And the two things together, this filtration is GT, and that's just the information about the background process, GDP and interest rates and so on, and the default history of the firm, and that's the information we're having. Good. The doubly stochastic random time, the idea is simple. It's a two-step process. I mean, you know, people in probability like to draw from urns if they want to visualize their models. So to generate a doubly stochastic random time, we have to sort of draw 2 times. In the first draw, we draw a realization of the economic environment or of the trajectory of the background process. And given that process, we then consider this as given. We consider a model where this hazard rate is now deterministic and equal to this given trajectory. And the second randomness is then really when does the firm with this given hazard rate really default. And formally, you're led to this definition here. A model has, if a random time tau default time is called doubly stochastic. If there is a background process gamma t, the hazard rate process, such that the probability that tau is bigger than t, given f infinity just means given the evolution of this hazard rate from the beginning of the world to the end is equal to x plus minus integral from 0 to t gamma STS. Of course, the gamma needs to be positive for that, and this integral here needs to be finite. So given the economic environment, we are having a model with deterministic hazard rate as we studied so far, but the economic environment can be also random, and so we have sort of a two-step procedure. Condition on the economic environment, we can apply the formulas we had so far, but then we have to average over it. Okay. Good. Maybe the best way to understand these times is to look at how you generate them on your computer. And I go on directly to the picture because from the picture you probably understand it best. You do a two-step thing. On the one hand, first you generate a trajectory of your hazard rate process. How to do that depends on which specific model you're using. A typical model people use is the so-called Coxinger-Ross model, which I will write down. Then, if you have a trajectory of the hazard rate, you compute the integrated hazard rate, gamma, which is just the integral from 0 to small t gamma STS. And we compute tau as the first, and we generate, independent of that, a standard exponential random variable, and then we define tau to be the first time where this integrated hazard rate process, this is this guy here, is bigger than the exponential random variable. So that's the E. We have this hazard rate process, and the first time that the process gamma is bigger than E, that's here 6 point something, that's our tau. That's how you can sample them, and this lemma here is just telling us that this way of sampling them is really the right thing to do. Okay, the next thing is how does pricing work here? And the key message is, I want to convey to you, is that this idea we've seen before, namely that the pricing of defaultable bonds can be viewed as a pricing problem for default-free bonds if we adjust the interest rate, that can be carried over. That was quite useful. I mean, this observation is now 30 years old or something. It's originally due to David Landau, but at that time that was useful because people had sort of a lot of experience already with default-free interest rate models and how to compute bond prices in those, and discovering that you can use the same type of mathematical techniques to deal also with defaultable ones was quite useful. You have reduced the problem to something which you already solved. Maybe some of you know this joke. You have a physicist and a mathematician, and both of them are given 2 pots of water and a camping stove, and they have the task of boiling 2 pots of water. So the physicist switches on the stove, takes the first pot, puts it on, lets it boil, puts it to the side, takes the second one, puts it on, lets it boil, and has done it. The mathematician comes, switches on the stove, takes the right pot, puts it on the stove, lets it boil, then he takes the left pot, puts it to the right side and says, now I've reduced the problem to one which I've already solved. And in a similar way, this is here also. People were, of course, quite happy that they had reduced this pricing problem to something which was already solved. So to explain these results, we consider an arbitrage-free market model, omega f filtration ft, and a pricing measure q, and the prices of all default-free securities, in particular of all bonds that do not default, are assumed to be ft adapted, and we have a default-free savings account. Tau is this default time of some company, and we assume that tau is a doubly stochastic random time with background filtration ft, right one, and hazard rate gamma t, and the price of all securities is given by this expression. Now, pricing formulas we cannot price everything, but as we've already observed, when we looked at our bonds and credit default swaps, we need to understand essentially a few building blocks, and then we can, at least many portfolios, we can reconstruct from those. So the pricing of bonds and credit default swaps can be reduced to the pricing of these two building blocks, the survival claim that pays us something if default does not happen, for instance, 1 in the case of a defaultable bond, and 0 otherwise. There are also other interesting survival claims. For instance, when it comes to counterparty risk, then it could be a derivative security where we get the payoff if the issuer of the option has not defaulted, and otherwise we might get nothing. But here we will mostly take x equal to 1 today. And the payment at default claim that pays us something directly at the default time, provided that default happens before some maturity. And the defaultable bond, as we've just seen, is a combination of the survival claim that models the payments if default has not occurred, and payment at default, which gives the recovery payment. Good. And the key result is this one that shows that the pricing of these building blocks can be reduced to a pricing problem for default-free claims with adjusted interest rate. So define the adjusted interest rate, RT, as small rt plus gamma t, and then under the above assumptions, so in particular if tau is double stochastic, the pricing of the survival claim, that's the price of the survival claim, to have the discount, we get x if tau is bigger than t, and we compute the condition expectation with respect to the filtration which contains everything, default history and background information. And that's provided the default has not yet happened, we have to compute the expectation of the discounted payoff x, but now in the background filtration, in particular if x is 1, we just have a default-free bond price, but with the adjusted interest rate. And the similar pricing principle also holds for payment at default claims. Okay. Maybe you bear with me 2 or 3 minutes, then I'm done for today. Applications, you can apply this to corporate bonds, and we can compute these prices. What is maybe interesting here is then we can also compute credit spreads. And what is interesting is that if you look at credit spreads over short time horizons, or here at instantaneous credit spreads where you really look at the spread of a bond which has maybe a day to go, but it's an approximation for a 2 or 3 month spread, you see that this spread is equal to loss given default times risk neutral hazard rate, as we had that before for our CDS. This is typically bigger than 0, so in these models you avoid the problem of the structural models. Alex pointed out that short-term credit spreads are unrealistically 0. In these models, this is typically not the case, at least if you use a reasonable model for gamma t. You can price credit default swaps in that setup. What you get is here an expression for the fair spread. And this expression is very similar to the one we had before for the models with deterministic hazard rates, only that there's sort of always an additional expectation there where we have to average over this R and the gamma here, and the same thing down here. But it's a straightforward generalization of the models with a deterministic hazard rate. Good. What is left, and then maybe I have to steal 5 or 10 minutes tomorrow mornings from Alex, is of course, are there reasonable examples, specific parameterizations, where expressions of this form here can be computed nice and easily? The answer is yes, there are, in particular in the field of so-called affine models, like the Cox-Ingersoll-Ross model. And I will spend, if Alex permits me, the first 10 minutes or so tomorrow morning to quickly show these formulas, and then we move on to portfolio products. So thank you for your endurance. Good. So what I want to do with you in the very last session of this week is to conclude the story from yesterday afternoon about the models with stochastic hazard rates, and to talk about counterparty risk. And concluding the story maybe means, to begin with, to come back to why we're interested in this at all. Yeah, that doesn't matter. Frank asked me this morning over breakfast. So you see, we're working all the time, and I thought maybe I come back to this a little bit, because what he mentioned, and of course he had a good point there, is that he could see that what I was doing yesterday afternoon, or we were doing this context of credit risk models of introductory chapter, had a lot to do with valuation and not so much with risk management. And what I want to explain to you is that it is an important part which you need to do if you want to do risk management for bond portfolios. So this goes back to sort of what we did in market risk in general. So you're an insurance company, and you're standing here at time t0, and maybe then you have a time t1, and you're interested in the loss distribution of your portfolio. And for simplicity, your ground portfolio consists of one single defaultable bond. So we want to find the loss distribution now. The value of this bond, if you go back to time t1, then the value will be equal to some, thank you, Paul, function g, that's our general mapping notation, of risk factors. And now what would be natural risk factors sort of here to consider? It would be probably some interest rate, RT, so that's interest rate, which is changing interest. And it will depend on the credit spread of the bond, or on the market's estimate of the creditworthiness of that firm. This is affected both by the fact if this firm has maybe really become a little bit riskier between T0 and T1, and it has to do with risk aversion of the market. Now, these two things cannot really be separated that easily, but it will depend on some, and that was what we typically call, they call it now psi t, and that is the default intensity, and that is a measure for the and that measures of the credit quality, that can be the market's perception and perhaps, if this time horizon is long, it will also be affected, of course, by the fact if default has happened or not. So maybe I put this outside. So this is true only if tau is bigger than T1. And so what we need, if we want to do that, we need to find this function g. And we need a model, okay, a model for random interest rates. We can write down a process. And we need a model for this default rate, and we need a pricing model that allows us to turn, sort of, given these realization of these numbers at time t1, into a price. And that is basically what I did yesterday. So if you think about simulation, you would then draw, if you, for instance, to begin with, say interest rates are maybe constant, we would draw various trajectories of this default intensity. So these are all paths of psi. And for each of these pi, we would then get a price of this bond.
So in a way, this is like a mortality rate?
This could be like a random mortality rate, yeah. Only that maybe with mortality, if you go from one day, if you make it, consider it over a horizon of 10 days, you can probably consider it deterministic. But if you would want to do this over a longer time horizon, you would say maybe you have a random mortality rate. It's exactly the same. And so that's why I said yesterday we need these models for stochastic hazard rates to be able to come up with a bond price in a world where the default intensity, or if you want, you can think about this psi also as a short-term credit spread, is fluctuating randomly. And then we can draw various of this path. For each of these, we get some value of the bond, and then we can compute value at risk or expected shortfall or think about hedging or whatever. And that's why having these valuation models is important, and that's why it is important to have valuation models where the default intensity, hazard rate, or short-term credit spread turns out to be more or less the same thing, is random. There is an additional small twist here, which is maybe also important to mention once. Namely, when you do that, you also have both measures around. Well, there's an old joke about probability. Probabilists using always different probability measures, and they all call them P. In financial mathematics, it's a little bit better. At least we call them P and Q. But that means that you have to vary which ones to take. I'm making this point. It's not just academic rigor or something. It is really important to people in practice. For instance, when those of you who still use the economic scenario generator of Berry and Hibbert, do you know how it's now called, that it's owned by Moody's?
It's still called an ESG.
Okay, it's still called an ESG. They worry a lot about getting exactly this point right. Namely, when you generate these scenarios here, you have to look at the P dynamics of psi. However, when we then take a realization of the default intensity and compute the bond price, then we need, so when we're standing here and then we sort of continue to look into the future to price the bond, then we would need the Q dynamics of the psi, and ideally these two would be consistent. Okay, that's why we're doing that, essentially why we want these models with random hazard rates, and why such things are needed to do risk management for a single bond, and of course also for bond portfolios. Maybe at some point we should really work out an example, but okay. That's one that doesn't work. Okay, that was the part on operational risk. Okay. Good. So now back to this. Which one is it? Okay. Good. Yeah. Well, you have the slides anyhow.
That's my job today.
Good. A little bit more light would be good, Paul.
It's called housekeeping service.
Okay, good. So that's why W stochastic random times. And, well, I recall quickly the definition and the construction. Tau is W stochastic, a random time. If there is some FT-adapted process gamma t, the hazard rate, and we will see it's closely related to short-term credit spreads, such that given that I know what the hazard rate is now and in the future, the probability that tau is bigger than t is just x plus minus integral from 0 to t gamma SDS. So as I explained yesterday, this is really a two-step thinking. That's why also doubly stochastic. In the first step, I generate my hazard rate, and given the hazard rate, I'm then considering consider this as deterministic, and I'm then sort of back to this survival analysis models with deterministic hazard rate. And that underlies also the construction or the simulation for these things. The algorithm is based on the following result. Paul mentioned, suggested I should recall it maybe for all of you. So what we do is we have the following result. We need to generate such a hazard, such a doubly stochastic random time. We need two things. We need a simple exponential random variable and then a trajectory of the hazard path, and these two have to be generated independently. And given that we have these two ingredients, we can consider the integrated hazard, so the integral from 0 to t gamma s ds, and then we simply say tau is the first time that the integral from 0 to t gamma s ds is bigger or equal to e, so it would be just the generalized inverse of the integrated hazard process evaluated at e, if you want to be fancy. But we take the hazard rate to be strictly positive, so it's just the inverse. So if you let capital gamma t equal to the integral from 0 to t gamma s ds, then tau is equal to gamma to the minus 1 of e. That's how you would simulate them. You first generate your exponentially random variable, you generate the trajectory of the hazard rate, and you return the tau as given here in 0.3. And it's also clear why this is doubly stochastic. You have these two mechanisms. You have the sort of, if you want, idiosyncratic generation of the exponential random variable, and you have the generation of the trajectory of the hazard rate process. And that's the picture we talked about yesterday. Just maybe something which may come surprising to you, the hazard rate itself, we will model it, for instance, by a Cox-Ingersoll-Ross process, so that's a diffusion that looks like that. But of course, if you integrate over it, you get something relatively smooth, and what is plotted here is the integrated hazard rate process. In the picture, it's a hazard rate process that may jump, and the jumps of the hazard rate are the kings in the integral. Good. And then, as I said before, what we want to do is we want to compute bond prices, and we derive pricing formulas. So what we need to compute are expressions as they're given in 61 here, expected value under a martingale measure of x of minus integral from small t to capital T rs ds given the payoff. Now, in the simplest case, we consider a survival claim that pays us 1 if the firm is alive at the horizon date capital T and 0 otherwise. So we would have to compute the expected discounted value of the survival. And in this situation here, it's sort of important that we keep the term with the interest rate inside the expectation, because this theory is, of course, able to accommodate stochastic interest rates, which is important for bond portfolio risk management, because at least over longer time horizons, interest rates are random. And what we've learned, and now we just consider only the first term, is that the pricing of such a term here is essentially, that's the price we have to compute of such a survival claim with respect to the information about default and about the background processes. And mathematically, it's the same as computing the price of something in the default free world. That's this expectation here, but with a higher interest rate. And of course, we have to do this only if the firm is still alive. There is a similar relation for payment at default claims, which we need, for instance, to compute the value of the default leg of a credit default swap. I talked about this yesterday. I think today I suggest that we focus mostly on the survival claim, because this is notationally a bit easier. Okay, and then we could study various applications, corporate bonds and credit default swaps. And okay, the nice thing was, for instance, for the credit default swap, we really saw that the fair swap spread we get is just very similar as the one we had in the models with the deterministic hazard rates, only that we always have to average over the path of this R and gamma here, and the same thing here. So there's an additional layer of randomness. What is interesting is that if we take swaps with a very short time to maturity, then the fair swap spread converges to delta times gamma t. Delta is a loss given default. And that's why I said if you want, you can interpret the risk-neutral default intensity as something like a short-term credit spread. So the spread of a bond which has only a few weeks to go or something like that, taking into account, of course, loss given default. And another interesting thing is that in these type of models, this quantity is going to be positive, whereas in the Merton model and in many other of these firm value models, this quantity is going to be 0 for capital T close to large T, which is why they're not so good for managing the risk of bonds with a short time to maturity. Okay, so what remains is, okay, how can I compute expressions of this type? At least in some special model, because so far we've just said we can reduce it to some simpler situation with deterministic interest rates. And I want to just show you quickly one class of models where this works. So typically when you set up a model, you will say, okay, I have this, I have an economic state variable, and the default intensity is a function of that state variable or is equal to that state variable. And so particular, the adjusted interest rate is a function of that state variable. Interest rate and hazard rate are, and then the sum of the two are also. And we want to compute expressions of this form. And we want to be able to do this easily. And we consider in particular the case where the G is just equal to 1, because that's the case of a bond. So the small RT is the default free interest rate, and that can be random in that context. Okay. It doesn't have to be, but it can be. And of course, if you want to do, say, risk management for bond portfolios, it makes a lot of sense to treat it as a random variable, because you have interest rate in there as well. Okay. And it should depend on the same set of factors. In the theory, it could be also multidimensional, but in the easiest situation, it would be a one-dimensional factor. Okay. Good. And the Coxinger-Ross, or CIR model, was originally modeled for the short rate of interest. It's also known as square root diffusion for the obvious reasons, because there's a square root in here. What you do is you say, okay, this factor psi, deep psi t, has two terms. It has a drift in there, and it has a diffusion component, so this is Brownian motion. Let's look a little bit at the form of these dynamics. I will also generate a few paths for you later on. The first thing you see is that this is sort of the systematic term in the dynamics of it, and this is the noise term. So the systematic term has the following thing. The kappa is typically positive, and the theta bar is some long-term level of interest rates, maybe whatever, 3%. Whenever, or some long-term level, when it's interest rate model, whenever the psi is bigger, the theta bar, you have a tendency to go down. Whenever the psi is smaller, you have a tendency to go up. So that's why this is called mean reverting. And trajectories will fluctuate around that theta bar. But of course, they will also always be driven away, because there's some noise. And the noise is modeled by the second part here. And there it's some volatility and some square root of psi to dwt. The square root is in here. Well, you could have a normal psi t, but then the model would be not, without the square root, would be not tractable anymore. You can omit it completely, then you would have the Vasicek model, but then you would have the problem that you have a model which can become negative, which is, in the current environment, sort of okay for interest rates, but which is sort of total nonsense for hazard rates. It makes no mathematical sense. But here, this stays positive, at least if the parameters are reasonable. Otherwise, it can reach 0, but it will not become negative. If kappa theta bar is bigger than 1/2 sigma square, then the model will never reach 0. Good. And in these models, you have an explicit formula for the price of a defaultable bond. That's of the form exponential of alpha times time to maturity plus beta times of time to maturity times the current risk factor or interest rate. And alpha and beta follow some complicated expressions. Just they are there, and they are known explicitly. So you can compute this, and because sort of the log of this expression is affine, one also talks about affine models. That's yeah, well, okay, at the moment it's a mathematical result. If you have, it would be a Q integral in pricing application. If an expectation of this form then takes this value, but it would be a Q expectation. So the message is there are models like Cox-Ingersoll-Ross where these pricing formulas which I gave you can be evaluated. So where this G which we had down here is sort of known explicitly. And the arguments would then be the psi T1 in here. Good. You can make things more complicated. The psi may jump. The psi, you can do it for payment and default claims. I jump over jumping psi, but I want to show you one last picture. And that gives us credit spreads for default with zero coupon bonds. The current value psi 0 is here about 5% sort of. Interest rate is 6%. It's an old example. Loss given default is 0.5. And here we have various recovery assumptions. That is the recovery of face value. That's the recovery of treasury. That's the recovery of face value. For small times to maturity, they all give you the same value. That's zero recovery. And then the credit spread is the largest because we lose most in default. For the other models, the credit spread is always the same for short times to maturity, but if time to maturity gets very long, they differ. Paul?
Just quickly, so what's the ordering? RM is one we haven't discussed.
RM is one we haven't discussed. It was wrong in the picture I had. That's why I could remove the label but not add new ones. In the new book, it's correct, but only Sam has that figure. So that is the recovery of treasury, and that is the recovery of face value.
Which are the two you mentioned?
That's the two that I mentioned. It's interesting that here credit spreads can, with these parameters, in very long time to maturity, even become negative. The idea is the following with the recovery of face value. You get money immediately at default, and when the loss given default is quite small and interest rates are high, it can be better to get 50% of your money after 2 years than all of it after 20 years, which is why this may happen. So when you have very long times to maturity and high interest rates, this model might not be so good, but at the moment it's probably not a problem. Okay, so now that's the bit which Alex did with you.